Okay, hi everyone. So this is Stat 200, Lesson 12, Correlation and Simple Linear Regression. So if you remember, correlation is kind of discussed earlier in the semester, but we use something called Pearson's R, which measures the correlation between two quantitative variables. So when we're talking about a sample, we use the symbol R, and then when we're speaking in terms of a population, we use the symbol rho, which is similar. It looks kind of like a P, but it's a little bit different than a P, but we call that rho. And then just some properties of R. R is between -1 and +1. So for a positive association, R is greater than 0, and for a negative association, R is less than 0. And then if there's just no relationship between the two variables, R equals 0. And the closer R is to 0, the weaker the relationship is. And then just the opposite, the closest to +1 or -1, the stronger the relationship is. So the sign of the correlation, whether it's positive or negative, provides direction only. It's also unit-free, so that means that it does not account for, say, if you're comparing pounds and ounces, those wouldn't change the correlation between two variables. And then the correlation between x and y is equal to the correlation between y and x. So it doesn't matter which variable is the y variable or which variable is the x variable, they will still have the same correlation. So here's just a chart evaluating correlation coefficients. So it shows a very weak relationship would be between 0 and 0.2, and then going up the spectrum, a very strong relationship would be 0.8 to around 1.0. And then if you were just flip this, so you could also do this with 0 and -2, that would be a very weak relationship, and then a very strong negative correlation would be -0.8 and -1. So we can do hypothesis testing with correlations. So first we're going to check our assumptions and write our hypotheses. And that is that both variables must be quantitative and the relationship between x and y must be linear. And then our null hypothesis would be that rho is equal to 0. And our alternative hypothesis would just be that rho is greater than, not equal to, or less than 0. So then we're going to calculate our test statistic, which we will use Minitab software, like statistical software like that, to calculate the test statistic. And similarly, the p-value will be calculated using Minitab as well. So once we have our p-value, we can make a decision whether to reject or fail to reject the null hypothesis. And then we can state a real-world conclusion after. So with simple linear regression, we use this to predict a response variable. So here we can use one or more explanatory variables to predict the response variable, which can be y. So if you remember from algebra courses or just other math courses, for example, you've probably seen the similar y equals mx plus b. It's very similar to that. So your predicted value of y is equal to your y-intercept plus the slope times the x, which is your explanatory variable. So if you don't remember what slope is just a measure of how steep the line is. It's also the difference between it's a change in x over a change in y, which is also known as rise over run. And a positive slope is a line moving from bottom left to top right, as shown in the little graph there below. And then a negative slope is a line moving from top left to bottom right. And then the y-intercept is just the predicted value of y when x equals 0. Sorry, that should be the predicted value of y when x equals 0. Of y when x equals 0. There we go. Sorry about that. Okay. So just some assumptions of a simple linear regression. So the first one is linearity. So the relationship between x and y must be linear. So there must be a straight like just like a linear pattern between the two variables. And then the second one is independence of error. So that's just saying that there is not a relationship between the residuals and the y variable. So you just want to make sure that those two are independent of one another, and that they don't, the residuals and the y variable don't relate to one another. And then next is just the normality of errors. So the residuals must be approximately normally distributed. So if you remember that bell-shaped curve as we discussed previously, and equal variances, so the variance of residuals is the same for all values of x. So this is similar to what we've done in the past. We do a confidence interval for a slope. So our sample slope would be, if you remember, we had a sample statistic where our sample slope is. So our sample slope will plus or minus our t star times our standard error of the sample slope. So it's very similar to what you've done before in the past with confidence intervals, just with different variables or in here. Just remember when you're calculating your t star, just remember to use a degrees of freedom that is equal to n minus 2. So it's just sample size minus 2. But then other than that, it's pretty much similar to what we've been doing in the past. So coefficient of determination. So the coefficient of determination is the amount of variation in the response variable that can be explained by the explanatory variable. So it's also denoted by r squared, and you just calculate this by taking r and squaring it. So it's pretty simple. So if you're given the r, you just square it, and that will be your coefficient of determination. So something that you should be aware of when looking at correlations is the influence that outliers have. So most of the time when you think about an outlier, you'll think about it as skewing the data, and you'll think of it as an outlier decreasing the value of a correlation, and then it weakens the relationship. But in other times, it may increase a value and improve a regression relationship. So that would be called an influential outlier. So if you'll see in the first chart to the left and the bottom there, you see the influential outlier, which I circled on the top there. And that makes the line a lot steeper there, and it shows that they have a more positive relationship. When if you take that outlier out, it shows just a barely straight line on the bottom, which shows that there really isn't really a relationship between the variables. So just something to be aware of. And then extrapolation is just when you're using your regression equation to estimate the response of a data point when the value for its explanatory variable falls outside the range of explanatory variables. So for example, an example I like to use for this is when you're looking at the heights of adults and you want to try to estimate the adult or the height of a child. So you couldn't use this range of data that you've collected on the heights of adults to estimate the height of a child, because it's just not, it's just outside the range of the data that you've collected on adults. So if you wanted to estimate the height of a child, you'd have to collect data on children's heights and then do it from there. Okay, so that was pretty quick. We just moved through everything. So this is the first review question. So the plot line shows this regression equation. So when x equals 0, what is the predicted value of y? So take a moment and I'll go over it in a second. Okay, yes, C is our answer here. So when we're looking at, when we're trying to predict the value of y when x is 0, we just want to look at our y-intercept here. And our y-intercept in the equation is 6.5. So, yep, that's good. So our second review, the correlation between quiz averages and final exam scores was R equals 0.60863. Calculate the coefficient of determination, or R squared. All right, yes, good. C is our answer here, so we're just taking our R, which we are given, and squaring it, and we get 0.3704. So great. So this is our last review question. So just calculate the confidence interval for a slope using the values given. So I put the equation for the confidence interval up on the right corner, and then the values that you will need from the data in Minitab. Okay, great job. So we take our slope and we add and subtract that to our margin of error, which is just our t star times the standard error. And then once we add and subtract the margin of error to the slope, we get 0.523 and 1.04. And we can just conclude that by saying that we are 95% confident that our slope is between 0.523 and 1.084.